Okay, today we're talking about Chapter 6, Section 3, Simplifying Radical Expressions. Alrighty, so let's see. I'm going to do a lot of snipping there. Maybe not. We'll just do the properties, because we can get to the examples of these properties in the examples, as opposed to the paragraphs there, I think anyways. Well, we hope so. Alrighty, so the multiplication property of radicals, and these are kind of tiny, so let's go ahead and make these a little bit larger. It's just the exponents there, or not the exponents, the index there. All right, so let's try this. So multiplication property of radicals, we're going to let a and b represent real numbers such that the nth root of a and the nth root of b are both real. Then the nth root of a times b, we can split it into the nth root of a times the nth root of b, or vice versa. We could have the nth root of a times the nth root of b, and that's going to be equal to the nth root of a times b. And then we have some customary rules here. So simplified form of a radical. We need to simplify radicals, and they must follow these rules here. So the radicand, right? The radicand is the number inside, has no factor raised to a power greater than or equal to the index. So we'll see an example of that. Number two, well, okay, we'll see an example of that, but I'll also try to explain it. So the radicand again is the inside. Right. We can I guess that's what the paragraphs are for, huh? Let's actually do that. This is it's one of those cases where it turns out the um, the publishers know what they're doing. Put this over here, and we'll put this over here. So we have the expression the cube root of x to the fifth. It fails condition 1 because the inside, the x to the fifth, is greater than or equal to the index, which is 3. The radicand does not contain a fraction. We see that we have a fraction, and there are no radicals in the denominator of a fraction. And of course, we've seen things, or at least we've heard, or I mean, you made it into college. You did this in high school, where you rationalized the denominator. Okay, and of course, this fails that condition as well. So let's put these into practice now. This seems, yeah, that's pretty short. Let's just go ahead and snip this whole darn thing. There's no point in me trying to reinvent the wheel here, huh? So this reads that to simplify the expression, assume that x is greater than or equal to 0. So we have the square root of x to the ninth. Well, we know that the expression x to the ninth is the same thing as saying the square root of x to the eighth times x, right? Because x to the eighth times x, we have the common base, and then we add the exponents. 8 plus 1 is 9. Alrighty, well, is that the solution? Hmm. I wonder if this is another case where it cuts it off. Yeah, I think it, well, heck. I meant to actually ask about this because for some reason the textbook is kind of cutting things off. So with that said, let's just not let us actually reinvent the wheel instead. Alrighty. So starting from pretty much where the problem uh, kind of let off, we know that we can rewrite the square root of x to the ninth as x to the eighth times x, right? Because x to the eighth times x is x to the ninth. We know that we can say the square root of x to the eighth times, let's fix that, it looks a little ridiculous, times the square root of x, right? Well, what is the square root of x to the eighth? Well, that would be x to the fourth, right? Because it's what you take the 8 and divide it by the index, and the index here is a 2, so 8 divided by 2 is 4. So it'll be x to the fourth times the square root of x, or we can just simply write it as x to the fourth on the square root of x. We'll have to put the multiplication symbol there. And that's weird. Yeah, it cuts it off. I don't know. I don't know. Alrighty, so let's do example 2. And we're just going to assume we're going to reinvent the wheel every single time now, because if I recall, we have had a lot of issues with this textbook, it seems like. Alrighty, so B, simplify each expression, assume all variables represent positive real numbers. So A, we know we can split up into, first of all, it's the fourth root of B to the seventh. So I know I can rewrite this as the fourth root of B to the fourth times B cubed, right? Because B to the fourth times B cubed, well, that's B to the seventh. And then I know I can also rewrite this as the fourth root of B to the fourth times the fourth root of B cubed. Well, what is the fourth root of B to the fourth? Well, that's just going to be B. And then times, okay, I don't have to put that there, times the fourth root of B cubed. Okay, so that is A. And then B, we've got the cube root of W to the seventh. So we've got, let's go ahead and split this up into, and well, let's do this actually. Let's just go ahead and write this, and then we can see if we can't find as a pattern here. Okay, so what is my pattern that we've been seeing here? Okay, so on this particular problem, we have a 2, an implied 2 right there, right? And it's x to the ninth. So we split up into x to the eighth times x. Okay, so there's that. This the example A here, we had a b to the seventh. We split into a b to the fourth, and then a b cubed. So, well, and in example B, we had a w to the seventh. I split it into w to the sixth times w, and of course z to the ninth stayed the same. So what's the pattern that we're seeing here? Well, what I'm doing here is I am finding the largest multiple of the index. Okay, so in this particular case, my index is a 3. So what is my largest multiple of 3 that will go into 7, because w to the 7th, and 9, z to the ninth? Well, it will go into 7 twice, which it'll go to 6, right? And that's where I get w to the 6th from. And then I have that 1 w remaining. And then the z to the ninth, well, 3 does go into 9, so we can just keep that the same. So what I'm going to do here is I can now split this up into I can essentially, and I'm gonna not write it separate like I have in the past 2 examples that I did. I'm just gonna go ahead and say, okay, so I'm gonna take the cube root of w to the sixth. So what is the cube root of w to the sixth? Well, that is going to be w squared, right? So we're gonna put the w squared on the outside, right? And then what remains on the inside is w. And I don't need it that large, so do w. Right, and that takes care of these two. And then we have z to the ninth. Well, what is the cube root of z to the ninth? Well, that's just going to be 9 divided by 3, which is 3. So it's going to be z cubed. So z cubed. Right, and that takes care of example B, 2b. Okay. Now we're going to deal with things that aren't necessarily variables. And this is where remembering your perfect squares and your perfect cubes come into play. So, in the square root of 56, does the square root of 56 have a perfect square factor in it? Okay, well, we have to ask ourselves, well, we got 28. No, we can factor this into 8 times 7. Okay, so we can factor this into an 8 times 7. That doesn't necessarily help us right now, but we know that 8 can be written as 2 squared times 2, right? 2 squared is 4. 4 times 2 is 8. And then we have the times 7. So we've now essentially set this up like the previous examples where we have perfect squares inside, okay? Because again, we have the implied 2 here, so it's a square root. So what is 2 squared, or the square root of 2 squared? That's just going to be 2, square root of 2 squared. And then it's going to be divided by the square root of, well, 2 times 7. We can just simplify that as 14. Okay, so that's that. Example 4 is even, I would say it's even easier to be able to tell what the perfect square inside is, right? 25, not 25, 50 can be rewritten as 25 times 2, right? Well, we know that 25 is a perfect square, so we could take the square root of 25, which is 5, and that goes on the outside of the radical. 5 times 6 is 30, so we have 30 on the square root of 2. And because I feel like I just kind of hand waved through that, I'm just gonna go ahead and snip this just for fun. Put that down there. All right, now we're getting into some fun stuff, and yeah. Alrighty, fun stuff. So we have the cube root of 40 x cubed y to the 5th z to the 7th. Alrighty. So first thing we have to do is figure out, okay, so 40. Does 40 have a perfect cube factor? Okay. Well, if you recall, I mean, what's the example we kind of just did, right? 8. 8, if we look back here, right? This is, 2 cubed, right? 8 is 2 cubed because 2 times 2 times 2 is 8. So with that said, we look at 40. Well, 40 is 8 times 5. So let's go ahead and just write that out. Let's go ahead and write that out as, all right, I'm not going to write the radical yet because I have this nasty habit of making my radicals too large or too short. So let's just go ahead and write 40. We're going to write 40 as 8 times 5. Okay, and again, keep in mind we're taking the cube root, so we have x to the cube or x cubed, so we can just keep that as x cubed. So keep that there. And we have y to the 5th. Well, what is the largest multiple of 3 that will go into 5? Well, that's easy. That's just 3. So we're going to have a y cubed times y squared, right? So again, this y cubed times y squared is indeed y to the 5th. I'm just writing it this way so I can factor some things out, or not factor things out, so I can take these numbers out of the radical. And then we have z to the 7th. What's my largest multiple of 3 that'll go into 7? Well, that's going to be 6. So we're going to have z to the 6 times z. Now let's put our radical here, like this, right? Well, let's go back and change this 8 to a 2 cubed, right? Because I know 2 cubed is equal to 8. So now here I've got a perfect cube here, perfect cube here, perfect cube here, perfect cube there. So all those underlined in yellow I can take out. So 2 cubed, the cube root of 2 cubed is 2. The cube root of x cubed is x. The cube root of y cubed is y. And the cube root of z to the 6th is z squared. And then what remains is going to be the cube root, nice threes, the cube root of, looks like a 5y squared z. 5y squared z. And that's it. So it wasn't as bad as we thought it would be, right? But I mean, it's still a lot of stuff. Right. So order of operation. I don't think. Yeah, very short section. I think the next section is even shorter. So another pretty good week for you, the student. Right. So I just got done with an hour and 20-minute lecture, and those poor students, that's an applied calculus course, they have to sit there and watch it. Maybe not all at once, because I certainly wouldn't either, but they got to watch that, whereas we're probably going to be done in 20 minutes. So use the order of operations to simplify the expression. So the order of operations to simplify. So we can do A in one of two ways. Okay, well, Yeah, we can do it in one of two ways. But what I would propose is let's just go ahead and take care of the fraction on the inside, right? A to the seventh over a cubed. Well, I know I can just rewrite that as the square root of a to the fourth, right? Because I have a 7, a to the seventh over a cubed, right? A 7 over a cubed. Well, that's just a to the fourth, right? Well, what is the square root of a to the fourth? Well, that's just going to be a squared. Pretty easy. And b, right? If we want to do it the same way, which we are, I guess, we can take this and say, well, we're going to take the cube root of, well, this fraction reduces down to 1 over 27. Right? And then from here, we can take the cube root of the numerator, cube root of 1, over the cube root of the denominator, which is 27. Well, the cube root of 1 is just 1, and the cube root of 27 is 3. So we have 1/3. Pretty easy stuff. I didn't do B. Oh, I did do B. Oh, shoot. That was pretty quick. And then lastly, and to me, I think the problems with actual numbers are the hardest. The variable ones are pretty darn easy, I think. But this one, of course, we've kind of had a square root of 50 already, so this should make it pretty easy. So let's just go ahead and rewrite this as 7 on the square root of 25 times 2 all over 10. Okay. Well, I know that I can rewrite this as 7 times 5, because I know the square root of 25 is 5, on the square root of 2 all over 10. Well, 7 times 5 is 35, so I have 35 on the square root of 2 all over 10. And then my 35, well, I can reduce that. I know 7 goes into both, right? 7 goes into 35 5 times, so 5. Actually, I don't want to do that. I said that backwards. 5 goes into 35 7 times on the square root of 2. And then we have 5 goes into 10 2 times. So 7 on the square root of 2 over 2. And that, let me just double check. That's pretty fast. Okay, well, that concludes the lecture on Chapter 6, Section 3.